Today's lesson is about the rotation of conic sections. So far, the conic sections that you have been working with have all been in the form of ax squared plus cy squared plus dx plus ey plus f is equal to 0. Now, with these conic sections, what you should notice here is I left out this term right here, the bxy term. Essentially, our coefficient of b is a 0, so we really have 0xy in all of the conics that you have been working with. And when that's the case, then all of our axes that we have for our conic sections are going to be vertical or horizontal. So the transverse axis, conjugate axis, major axis, minor axis, axis of symmetry, directrix are all going to be horizontal or vertical. And that's going to give us a conic section in what we know right now. But what if I want a conic section to look like this? So I have this ellipse now, and this ellipse is essentially rotated, and it no longer has a major and minor axis that are horizontal and vertical. So here is my major axis, and here is my minor axis. And those are no longer horizontal or vertical. So what I know right now for writing the equations and being able to graph these doesn't apply if the equation is rotated, because how do I put something that looks like this, ax squared plus bxy plus cy squared plus dx plus ey plus f, into the forms that we know by completing the square? This bxy term is going to make that very difficult. So what we want to do is we want to then take our axes that we currently have, and we're going to rotate them. So here, if this is my x-axis and my y-axis, I'm going to rotate these. So rotate the x-axis a certain amount such that I'm going to make a new axis here, and I'm going to call this new axis an x prime axis, and I'm going to rotate it theta degrees. And I'm going to rotate the y-axis by that same theta degrees. And then here is my new y-axis, and we'll call this my y prime axis. And now my axes of my rotated ellipse are going to be horizontal and vertical with my new x prime, y prime values. So if I can take all of my variables in my original equation and find their corresponding variables in the x prime, y prime axes, then I can graph and do what I know how to do with my conic sections that I've learned so far in the previous lessons. Okay, so let's put that to work and see what that means. So essentially what we want to do is we want to eliminate the xy term, okay? So we want to eliminate this xy term, so the bxy term, and make the b value equal 0 by rotating our axes a certain degree, okay? These new axes you're going to see are going to be notated as x prime, and that should say y prime right there, and y prime. And then we're going to get a new general form here that is relative to the x prime, y prime axis. Okay, that equation then is going to look like this. And notice in this equation, we have our variables are all prime, so x prime and y primes. And we no longer have a bxy term, so that means we've eliminated that xy term by making the b value equal to 0. So we need to figure out the relationship between the x coordinate and the y coordinate to the x prime, y prime, and the theta value. So to do that, I'm going to draw a few triangles on the diagram, and then I'm going to ask you to try and find out some information about these triangles. Okay, so this coordinate right here, this coordinate can be called x, y, or on the x prime, y prime axes, it would be called x prime, y prime. So if I'm talking about x prime, y prime, it's called x prime, comma, y prime. And so I'm just moving along. If I move along the x-axis and then move vertical on the y-axis, that gets me to that point. If I move along the x prime axis, vertical on the y prime axis, that also gets me to that point. All right, so let me draw a few triangles in here. So I'm going to drop a perpendicular from this point here on my x prime axis straight down. So go ahead and follow along with me on your diagrams. And with that perpendicular, I'm going to make this triangle. So you can see this yellow triangle right here. And this yellow triangle right here is a right triangle, right? So we have a right triangle there. Mark it a right triangle. And we know that the rotation from x to x prime here is theta. So this angle inside here of that triangle is going to represent theta. Okay. Then I'm going to draw another triangle. So let me draw another triangle in here. And I'm going to draw a perpendicular from this point here again. And I'm going to draw that perpendicular horizontally. Let me just make this a little smaller. So horizontally. So it hits that axis right there to make my right angle. And we're going to look at this purple triangle right there. So I have the yellow triangle, and then I have the purple triangle. And what I want you to do right now is I want you to think about the sides of those triangles and write the sides of the triangles in terms of x primes and y primes and thetas. So we're going to write the side lengths of the triangle, the purple and the yellow, and the only variables and information you can use are x primes, y primes, and thetas. Okay? So go ahead and pause the video now and see if you can write those sides of those triangles in terms of each of those. All right, now that you've had some time to think about that, well, let's see if you figured out the correct answers. So let me first work with the yellow triangle there. So for the yellow triangle, I have theta for my angle inside there. And I can write the vertical side by using the sine function. So for the vertical side, I can say that the sine, let me change colors here, that the sine of theta is equal to the opposite side, so I'm just going to call it A for right now, is equal to A over the hypotenuse. And I know the length of the hypotenuse. The length of the hypotenuse is from here to here. And that distance is the distance on the x prime axis to get up to this point. So that length there, all the way from here to here, is going to be x prime. So A over x prime. So that means that A is equal to x prime sine of theta. All right, so I'm going to change that. So my A is equal to x prime sine of theta. Similarly, the bottom of that yellow triangle, I can use the cosine function. And so the bottom of that triangle is going to be x prime cosine of theta, because cosine of theta is equal to adjacent over hypotenuse. All right, so now I have the yellow triangle, and now I'm going to look at the purple triangle. So for the purple triangle, I don't have any angles in there. So I need to find a way to get one of the angles that's in that triangle. There's a couple different ways to think about it, and it all comes down to geometry. Okay, so one thing that you can think about is that this segment here on the bottom of the triangle, this bottom segment right here, is horizontal. And so that means it's parallel to this bottom segment here. So I'm just gonna make a little dashed kind of line coming out of here. And then that you should be able to see that we have alternate interior angles. So if I go here to here, to here, those are alternate interior angles. So that means that this angle inside here, this little tiny one, that little tiny one is also going to be theta, because alternate interior angles of a triangle are congruent. Okay. Then the other thing that you can say is that this purple segment right here, the hypotenuse of the purple triangle, is perpendicular to the x prime axis. So since that's perpendicular, then I know that this angle inside the triangle there is going to be 90 minus theta, because the bottom portion of that right angle is theta. And then if that's 90 minus theta, and on the purple triangle, the other angle is a right angle, then up here at the top, that must also be theta, because the two non-right angles in a triangle are always complementary. All right, so now in the purple triangle, I have a theta value, and so I can figure out the different sides of my triangle in terms of x primes, y primes, and thetas. So first of all, the hypotenuse of that triangle is the easy part, because that is simply the vertical distance to get to my coordinate on the x prime, y prime axis. So that's going to be y prime. So the hypotenuse of that triangle is simply y prime. And then using theta, let me write this first one out. If I do sine of theta, the sine of theta is equal to the opposite side. So I'm just going to put opposite OPP over the hypotenuse, which is y prime. So that means that the opposite side is equal to y prime times the sine of theta. So that's the short side on the bottom here. So this short little purple side is y prime sine of theta. Similarly, the vertical side is going to be y prime cosine of theta. Okay, so now I've written each of the side lengths in terms of x prime, y prime, and theta. So you might be thinking, okay, so great, what the heck does that mean? Now I want to relate this information to the x and the y values. So I'm going to write one equation that's going to be x equals, and then something in terms of x primes, y primes, and then another equation that's going to be y equals, so I can change all my x, y variables into the prime variables. All right, so now let's look at our diagram and see where we can identify the x value. All right, so looking at the diagram, we can see the x value is the distance from here just to here. So it's not all the way across on that yellow triangle, but it's up to that point right there on the x-axis. There's our x value. So I know that it could be x prime cosine of theta, but it's not quite that. It's just a little bit less than that, just that much less. Oh, that horizontal distance, I know that up here. That horizontal distance is congruent to this y prime sine of theta here. So this bottom part and this right here are congruent. So this little section is also y prime sine of theta. So if I just subtract those two, if I take x prime cosine of theta, which is all the way to here, and subtract that y prime sine of theta, then I'm going to get the x value. So minus y prime sine of theta. Okay, see if you can figure out the vertical piece for the y value. So on the diagram now, the y value is going to be right here. So this whole section right here. How could you write this whole length that I just highlighted in blue in terms of just x primes, y primes, and thetas? So you can take a pause right now and see if you can figure that out. All right, so hopefully what you saw is that you can do the sum of this vertical purple segment right here and the vertical yellow segment of this triangle, because that yellow segment is congruent to this piece right here. So what we have is the yellow segment plus that purple segment. So we have x prime sine of theta and then plus y prime cosine of theta. Perfect. All right, so we found a way to write x and y in terms of x prime, y prime, and thetas. So now we can take this and plug it into our equation and convert all of our x's and y's into the prime variables. But what we do also need to know is we need to know what's that angle of rotation, because we need that angle of rotation to be able to evaluate the sine and the cosine values. Now I'm going to just tell you the formula for the angle of rotation, and then at the end of the video, I'm going to show you the proof of the formula. Okay? So the formula for the angle of rotation is simply cotangent of 2 theta is equal to A minus C divided by B. Now, some like to think about this in terms of tangent instead, because our brains are more used to using tangent instead of cotangent. However, there's an issue with the tangent equation, and I'll talk about that when I show you the proof. Okay, so we're just going to accept that angle equation right now, and we're going to take these 3 pieces of information. These are the 3 pieces of information that you need to know. You're going to need to memorize these 3 to be able to rotate a conic. Let's do an example. All right. Example number 1 says rotate the axes to eliminate the xy term, then graph using the new rotated x prime, y prime axes. So the first thing that you want to do in these kinds of problems is you want to find the theta value. So we're going to first identify the a, the b, the c values. And so knowing that our formula is ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, we can identify the a, the b, and the c values. So really I have no 0x squared, so it's really like a 0x squared plus xy plus 0y squared, and then plus 0x plus 0y minus 2. So that means that my a value is equal to 0, my b value is equal to 1, and my c value is equal to 0 from those three coefficients. So I'm going to go ahead and I'm going to plug that into my formula. So my formula is the cotangent of 2 theta is equal to a minus c divided by b. So I get cotangent of 2 theta is equal to 0 minus 0 divided by 1. So I get the cotangent of 2 theta is equal to 0. And so now I want to think about, okay, where is the cotangent equal to 0? So this happens when the cosine is equal to 0. And so that's going to mean this happens at pi over 2. So I have 2 theta, don't forget about the 2 in the 2 theta, is equal to pi over 2. And technically to get all angles, then you would say plus k pi. However, we just need the 1. We're going to take the smallest angle. So you just need the first one on the unit circle. Then we divide by 2 and we get theta is equal to pi over 4. Perfect. So now we know our theta value. With that theta value, we can write the x and the y equations that are going to go with our problem here. So the x equation is x equals x prime cosine of theta, which is pi over 4, minus y prime sine of theta, which is pi over 4. So sine of pi over 4. And then I can evaluate that. So x is equal to cosine of theta is root 2 over 2. So square root of 2 over 2 x prime minus sine of pi over 4 is also root 2 over 2. So root 2 over 2 y prime. So here is my x value that I'm going to be using in my formula. And now I need to find the y value to go with my equation. So using the y formula, I have y is equal to x prime sine of pi over 4 plus y prime cosine of pi over 4. And then I evaluate, so I get square root of 2 over 2x prime plus the square root of 2 over 2 y prime. Prime, not a dash, prime. And there's my y value. And from here on out, we're just going to substitute and we're going to simplify, okay? The longer your equation, the more complex it is. So just be patient as you work through these problems and take it slow. Okay, so I plug that all in to my original equation. So my original equation is x, y minus 2 equals 0. So in place of the x, I put the new x. So in place of my x, I have square root of 2 over 2 x prime minus square root of 2 over 2 y prime. Then multiply by the y value, which is the square root of 2 over 2 x prime, plus the square root of 2 over 2 y prime. Then I have minus 2 equals 0. And now I just have to multiply this all out. So you're just going to do the FOIL and multiply this all out. So square root of 2 over 2 times square root of 2 over 2. The square roots are just going to give you 2 and then over 4. And so you're going to get, I'll just write it as 1/4 x prime quantity squared. And so that's first. And then I'm going to do the first one times the second one. Well, you can see that these two are conjugates. So square root of 2 over 2 x prime times square root of 2 over 2 y prime is going to cancel out with negative square root of 2 over 2 y prime times square root of 2 over 2 x prime. So those two terms are going to cancel. And then I have to do negative square root of 2 over 2 y prime times positive square root of 2 over 2 y prime. So I'm going to get minus, and then I have 1, whoops, I wrote this as 1/4. That should have been 1/2 because I had 2 over 4. So when I reduced it, 1/2. Minus 1/2 y prime quantity squared. And then minus 2 is equal to 0. All right. And so I'm going to go ahead and put this into the standard form for the conic so I can graph it on my x prime, y prime axes. So what I have is I have x prime quantity squared over 2 minus y prime quantity squared over 2 equals, and I'm going to move the 2 over. And the denominators are the same, but I have a minus inside there. And so because I have a minus inside here, I know it's going to be a hyperbola. So I want the right side to equal 1. So I'm going to divide everything by 2. So dividing everything by 2, I get x prime quantity squared divided by 4 minus y prime quantity squared divided by 4 is equal to 1. And so this is now my standard form for the equation of my conic. And so I know that this is going to be a hyperbola. Okay, so now we're going to go ahead and graph it. So my angle of rotation was pi over 4. And so on pi over 4, I'm going to draw a new axis. So here's my new axis on pi over 4. And I'm going to do my best to get it on there. It's not going to quite go, but we'll pretend it's perfect. So pi over 4 there. And then my y-axis would rotate pi over 4 as well. So I'm going to do my best to get that. That'll move over to 3 pi over 4. Okay. And I'm going to label that rotation. So this rotation here is pi over 4. So it's clear what it is supposed to be. And now I'm going to graph my new equation on these axes because this is my x prime and this is my y prime. So from my equation, I know here that my denominator is 4. So that means that I can get my a squared is equal to 4. So that means that a is equal to 2. Also here, I know that b squared is equal to 4. So b is also equal to 2. And so I can graph. So if a is 2, okay, this is going to be really skinny on here. I'm going to change it. Let's change this to counting by 1 and then make this a 2, make that a 3, make that a 4, make that a 5. Okay, so if my a value is 2, then that means on my x prime axis, it's going to be a horizontal transverse axis. So I'm going to go 1, 2 units right there. And this coordinate then would be 2, 0 on my x prime, y prime axis. So 2, 0 on my x prime, y prime. Then -1, -2. So -2, 0 on my, for my other vertex. That's going to be my vertex. And then I can get my conjugate axis. My b value is also 2. So it's going to go here for my co-vertex. And then 1, 2 here for my co-vertex. So there's my box. And then I'm going to, from my vertices, I'm going to use my vertices to make my graph. So here I know that my equation of my asymptote is going to go through the corner of the box, right? So let's draw our asymptotes in. The asymptotes are going to be the original x and y axes through that corner of that box. Okay. And so here's my graph. There was one branch of my hyperbola. And let's see if I can do this, get the second branch of my hyperbola. Perfect. And there we have. All right, let's do one more that gets a little bit more complicated. It is not any different. It's just a longer equation. So here is number 2. All right, so the first thing that you want to do is you want to find your theta value. So to find your theta value, we need to identify the a, the b, and the c values. So our a is the coefficient of the x squared, so a is going to be 7. The b is the xy coefficient, so that's going to be -6 squared root of 3. The c is the coefficient of the y squared, so that's going to be 13. So go ahead and I want you to write the 3 equations, or find the theta value, and then write the equation for x and write the equation for y. So go ahead and pause the video right now and complete. All right, please check your answers with what you now see on the screen. And so now with these 3 values, you can go ahead and begin your substitution. And then if you want to draw your axes at pi over 6 right now, you could do that. So you know that theta is pi over 6. So you can draw your rotation at pi over 6 for when you're ready to graph it. So there's pi over 6 there. And there's pi over 6 here. And so these circular graphs are helpful for graphing these rotation of conics. They're called polar grids. So you can Google polar grid to get polar graphs for your homework if you'd like. Okay, so now we just need to go ahead and we need to do our substitution. So for a substitution, we're just going to go ahead and start plugging in. So I have 7 times x squared. So I plug in my x value, which is root 3 over 2 x prime minus 1/2 y prime quantity squared, minus, and then 6 square root of 3 times x, so root 3 over 2 x prime minus 1/2 y prime, 1/2 y prime, times y, so that's 1/2 x prime plus square root of 3 over 2 y prime. And as you can see, it's really important not to be sloppy because your x's and your y's can easily look like each other, especially with the primes next to them. So then plus 13 times y squared, so 1/2 x prime plus square root of 3 over 2 y prime quantity squared minus 16 is equal to 0. All right, then we need to go ahead and we need to expand this. So we're going to expand the square here, and then we're going to multiply that square by the 7. And then same thing, multiply these two terms in the middle together, the x and the y, and then multiply that by 6 square root of 3. Square the y value, multiply it by 13. So I'll give you guys a moment to go ahead and do that. So you can. All right, there's my first step. You can see I was running out of room. I had to go into a second line. And then we're just going to distribute the coefficients in, and then you'll work on simplifying and combining like terms. All right, so there's the full expansion, and now we're going to look for like terms. And when you're doing this, the whole point of doing this is to cancel the b term. So that means that all the xy terms should cancel each other out. So let's see if that happens right now. All right, so my bxy terms, I have this one right here, -7 square root of 3 over 2. I have -3 square root of 3. I have 13 square root of 3 over 2. And so looking at those three terms should cancel each other out. So if I get a common denominator, this one here, this -3 root 3 would become -6 root 3 over 2. So -6 root 3 over 2 plus -7 root 3 over 2 is going to cancel out a positive 13 root 3 over 2. So all three of these terms together are going to cancel out that bxy. And then I'm going to go ahead and I'm going to add together the other terms that I have remaining. So adding together the x prime squared terms. So I have 21 over 4 x prime squared. I have -9/2. I have 13 over 4. And those are my 3 x prime squared terms. And adding those three together, I have, let's see, 21 plus 13 is 34. 34 minus 18, because it's got to be 18 over 4, is going to give me 16 over 4, which is going to be 4. So I get 4 x prime squared. All right, and then all the three terms, I have 4 terms left, but I have my constant minus 16 at the end. So if I add together all of the y primes, oops, I forgot my squared right there, y prime squared terms, I get 16 y prime quantity squared, and then minus 16 is equal to 0. So with this then, I can put it into the standard form for the equation of a conic. So if I move over the 16 and then divide by 16, I'm going to get 4 x prime quantity squared plus 16 y prime quantity squared equals 16. Then divide everything by 16. I have x prime quantity squared divided by 4 plus y prime quantity squared divided by 1. You don't need to put the divided by 1 is equal to 1. So here is my conic in its conic form in terms of x prime, y prime. And so now I can take this and I can find, I know that it's an ellipse. I know that the a squared is equal to 4 because it's always the bigger denominator on the ellipse. So a is 2. B squared is equal to 1. So b is 1. And I know since the x is the first term with a larger denominator, then I'm going to move the a value on the x prime axis. So this is my x prime axis, this is my y prime axis. I'm going to change the values on here too because it's kind of small. So let's make this a 1, then a 2, then a 3, then a 4, and a 5. Okay, so I'm going to move 2 units here across on my x prime axis. So 2 units, that's my vertex, And then 1 unit is my co-vertex, 1 unit is my co-vertex on my y prime axis. And I'm going to make my ellipse. And so here's my ellipse. Beautiful. And so we are done with this lesson. If you'd like to continue listening, I will go over the proof for the angle formula that I just gave to you. All right, so here is the proof of the angle formula for rotation of conics. So what you see right now on your screen is you see the equation ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, with each of the x's are replaced with the x formula that we already proved. And then we have the x formula times the y formula. Then we plugged in the y formula, and that one's squared. Then we have the x formula, then we have the y formula. So the first thing we need to do is we just need to do a bunch of algebra, and we just need to expand all of this information, and then we're going to regroup. So I just go ahead and start by expanding. So I'm going to expand all of this information here. And my first expansion is this. And then you can see that I highlighted some different things. And the things that I highlighted are going to be like terms. So you can see here that the pink is going to be x prime squared variable, x prime squared variable, x prime squared variable. Okay. The yellows are y prime squared. So y prime squared, y prime squared, y prime squared. The purples are the xy terms, x prime, y prime terms. And then the greens is the x prime terms, and the oranges are the y prime terms. So I do need to continue to distribute. So I'm going to distribute everything, and then I'm going to regroup it on the next step. So let's see what that looks like. All right, so I not only distributed the rest of the way, but I also regrouped. So notice for the pink section here, we have this whole quantity here. Oops, wrong tool. We have this whole quantity. This is the coefficient, and that's the coefficient of the x prime squared. So I took all the x prime squareds and I factored the x prime squared out and wrote the coefficient all as 1. So then next we have all of the coefficients here of the x prime y prime term. And so that's the purple right here. That's kind of, the highlighter is hard to see on there, but I'll put a big box around it. So that's the purple. And that's the coefficient of the x prime y prime term. Similarly, I have the coefficient in yellow of the y prime squared, and I have the coefficient in green of the x prime, and orange of the y prime, and f is the constant. And notice that f is the same as the f. There's nothing else that changes with that constant value. Okay, so on the next step then, what we're going to look at is we're going to look at what do these values represent in terms of our x prime, y prime. So this stuff in pink here, this coefficient in pink, this is going to represent the a prime value of our new equation. The purple is going to represent the b prime value. The yellow is the c prime value, and so on. So if I set each of those equal to those values, now what I have is this, that a prime is going to be a cosine squared of theta, forgot my theta there, plus b cosine theta sine theta, plus c sine squared of theta, and so on for each of the values. Now notice I didn't put the b prime term in there. I have a, c, d, e, and f primes. The b prime is the one that we're most interested in. So when we rotate a conic, what we said is that we want to eliminate the bxy we want to eliminate the bxy term. So essentially we'd want that b value to become 0. So our b prime is equal to everything that you see here in purple. Okay, so if we look at all that stuff in purple there, we can see that b prime is equal to all of that stuff there. It's quite long, but we can simplify it using some of the formulas that we know from chapter 4, our trig identities. So if you look at what I have boxed in orange, those are both cosine theta, sine theta terms. And so I grouped those two together and pulled that out. So I get 2c minus 2a sine theta cosine theta plus b cosine squared minus sine squared. Now we think about this. Cosine squared minus sine squared, that's an identity that we know. Think about what it is. You should be thinking that it is the cosine double angle formula. Cool. Oh, interesting. Then we can also see that on the left, we almost here have the sine double angle formula, but it's just sine theta cosine theta. I need 2 sine theta cosine theta. So let me take this 2 here and put it with that 2 sine theta cosine theta, because now that becomes sine of 2 theta. And so now I have this. And now I can continue working with this equation. Okay, so we're going to take this equation and we're going to do our final step. So our goal, as we said, was to eliminate the x prime y prime term. Let me just go back up, leave a little bit of that on the screen. So we want to eliminate the x prime y prime term. And so we need to find a theta value to make the b prime term equal 0. So we really want this b prime right here to equal 0. So this b prime formula that we have from above, that just comes from right here, we want that to equal 0. So I set that equal to 0. And if I set that equal to 0, I can find a value of theta that's going to make that equation work. So it's just like something we could do in chapter 5 where we solved trig equations. So let's solve this equation for theta. All right, let's do it. So I just move things over, move over the b cosine 2 theta, and then I can divide by the sine of 2 theta and then divide by the negative b, and I get cosine 2 theta divided by sine 2 theta, which gives me the cotangent of 2 theta, and then equals c minus a over negative b, but I don't like having negatives in the denominator, so I'm going to rewrite that as a minus c over b. And this is the formula that I gave you. Cool. Now notice here, I put on the side, as we're doing this, we do want to think about this fact. Our denominator, we're dividing by the sine of 2 theta. So this implies that sine of 2 theta cannot equal 0. So let's think about, is this okay? Do I have to make a note of that and put a second case to be a special case of when the sine of 2 theta equals 0, I have something different? Think about that for a moment. Think about what angle would satisfy the equation of sine of 2 theta equals 0. Well, let's solve it. What would make sine of 2 theta equal 0? So sine of 2 theta is equal to 0. So where is theta, or where is sine equal to 0? Well, the sine is equal to 0 at 0 or 180 degrees. Well, then I would divide by 2, so theta is equal to 0. Well, if theta is equal to 0, then there's no rotation. So I wouldn't be even worrying about rotating because I wouldn't even have a b value in my equation. So we don't have to worry about that. Okay, cool. The other thing we should think about is at the very end, we also have a denominator. So my denominator is b. So that means that b cannot equal 0. Well, is there a case where the b value in my original equation would be 0? Hopefully you're thinking no, because if there were a b value, if there weren't a b value and the b value was 0, again, there would be no rotation. So this is a good equation to use because we don't have any cases that are special cases. Now, earlier I mentioned some people like to think about this as tangent of 2 theta is equal to b divided by a minus c. But this kind of poses a problem because now here, what you have to think about is, could a minus c equal 0? Yes, a could equal c. So if a equals c, then this poses a problem because we're going to get an undefined value for tangent. So that's why the cotangent theta equation is better. All right, now you know everything you need to know about rotating conics. Have fun.